So. All right, so last time we learned that home in both variables is left exact, right? So in particular, we don't expect that last map in the home sequence to be onto. However, in the case of split exact sequences, we can do this. So. Let A, B, C be arguments. Following conditions are fit. Number one. Suppose it's not just short exact, it's split exact. 0. This is split exact for every D. And 3. Split exact problem. So if you if this is short exact, you don't necessarily get that this last map is onto in either case, right? However, if this is split exact, not only do you get this short exact, in fact, it is also split exact. And in fact, it's the equivalence in the sense that these are split exact for every D, then the original one is split exact. So here we're going to show the equivalence of A and B. So actually, as opposed to the previous theorem that I did, here I'm going to do the covariant one and leave the rest for an exercise. We'll do this and leave A is equal to C as an exercise. So for A implies B. What do we know for A implies B? We already know 0 we know this part is already exact, right, by the previous theorem. So if we have this split exact, in particular, this is exact, and so this is exact by the previous theorem. So really, we can kind of get this in one fell swoop if we do the following. We just want to show that there's an H bar. There exists H bar from home RDC into home RDB. such that when you do H bar and then G bar, this is the identity on because that'll kind of get everything at once, because of the fact that this composition is the identity, that means in particular the G bar is onto and H bars are splitting, right? So that's really all we got to do here. Now, since the splitting fact, there exists H C to B such that when you do H and you do G, you get the identity equals C, right? And it's going to turn out that's really all we need. Since then because what happens here is we have this is oops, first and so first we go H from C to B to G. This is the identity. And how does the induced map go? Well, induced map just recall how this works. If you have, let's say, gamma going from B to C, then gamma, now we have to go from P to B, so we do gamma. I want to say, I need something here from A goes from D to B. How does this induced map work? Induced by this H and G? Well, we take gamma, and we're not going to do B, so we do gamma and H. Right. So that is to say, H bar of gamma is H gamma. And the way it works here is eta goes to, it's induced by F. B to G eta. So G bar. Notice that when you start with gamma, then this pushes on to H gamma, and then H gamma pushes on to GH gamma. But of course, remember this was the splitting, so this is the identity gamma. Therefore, so there's kind of a little explanation, if you will. that when you do, this is the identity on home R. Everybody okay with it? So there's what we need. If this is split exact, then our H bar is exactly. Okay. Now let's do B implies A. So now our assumption, and I guess I never get the letters and numbers right. So now we have the home sequence is split for all D. Splits for all day. So here what I'm gonna do, once again, is I'm gonna pick something that's gonna work out for me. I'm gonna pick D equals C. And I am going to let phi go from C to B. And I want this such that when I do G bar to this, I get the identity on C. So this is, of course, composition G phi, which is the identity on C. And so zero A B C. So basically phi is our split. Okay, any questions on it? See if you do the equivalence of A and C. It's very similar. It's just maps going the other direction. Okay, questions on that? Okay, here is. So you might, so split exact, very good, right? Everything's all encapsulated neatly, but we also have that if this is exact, and this is exact, we also have, if this is exact, then this one is exact. What conditions might you have that improve your situation? Well, here is a theorem that once again shows the importance of projective and injective. Here's the projective analog first. Let P be an R model. The following are equivalent. Number one, P is number two, if B from B to C is projective, I'm sorry, onto, then the induced phi bar from home R PV to home R PC is onto And C, there are three. If you have a short exact sequence, then this is short exact, then 0 into home I don't. Okay, so this gives me this gives me kind of an interesting characterization of projective in terms of covariant Hom, right? So following equivalent, this is projective. If this is onto, then the induced map from home PV to home PC is onto, and if you have the short exact sequence and P is projective, then you preserve short exact sequence. So it forces this last one to be onto. Now let me give you the analog for injective, and then we'll prove projective. So the injective analog is as follows, and this one is for contravariant theory. Let I be an normal. The following conditions are equivalent. One, I injective. Number two, if you have a one-to-one map, B, one-to-one, then the induced map in covariant what's the last word I'm gonna write there? Yeah. Yeah, kind of weird, right? But that's what's gonna happen. So that'll be fun to prove. And if you have a short exact sequence, letters, in short exact, then okay. So this is kind of the dual theorem. Injective works off of the contravariant Hom, and projective works off covariant Hom. But they're an analogous result. The only weirdness, I think, is, well, 2 and 3 are equally weird, but the obvious weird one is it turns the 1-to-1 into a non-to, right? Well, we've seen this kind of thing happen before in the contrarian case. So let's prove 674 and see if you can prove 675. Okay, so some of this is just by definition here. So let's first start 1 implies 2. Okay, so what do we have here? We have the field projective, and we have this is onto then the home map, the induced map on home is onto as well. So here's a situation. We have phi from B to C that is onto. And what we want to do is show that the induced map on home is onto. We know that P is projective. So what I'm going to do is I'm going to let something, alpha or something, be in, like, I'm going to call this alpha. I mean, that's, this picture actually sort of draws a picture of exactly what this means. Alpha is a homomorphism from P to C, right? As P is projected, there exists H from P to B such that when you do H and then you do phi, this is exactly alpha. Right? That's what it means projected. But notice that what this means is phi composed with H is alpha, and this is precisely the induced phi bar of H. So given an arbitrary alpha homomorphism from P to C, there exists an H. Given alpha and home R P to C, there exists H in home R P D such that phi bar of H equals alpha. So phi bar is on. Right, so this is really just chasing a definition. How about 2 implies 3?
Not just kind of free, like we get the first part from.
You mean for 2 implies 3? Yeah, this one won't be too rough because. And the 3 statement here, what we want to show is we're given 0, A, B, C. That was pitchfork and thing. You short it back. Now, what we already know that we get for free, if you will. Zero. This is exact. Here, I don't need anything about P being projective. This is true for any module, right? It remains to show P bar is on to. But that's part two. Right, so there's nothing much to that. We've already done the heavy lifting on this one earlier. Right. How about this? 3 implies 1. We need to show, we know that for, if you have an exact sequence, then the covariant sequence is short exact. Right? We need to show that P is projective. So to this end, okay, so we'll do 3 implies 1 here. So given any short exact sequence here, we get the induced Holm sequence. So we need to show that P is projective. So suppose we have here. So this is on to, we have P here. We need to show this lifts, right? Well, okay, so how can we deal with this? In part 3, I see something about short exact sequences. So this is kind of a piece of a short exact sequence. We have so I'm going to take this and I'm going to stretch it out into a short exact sequence where the first map is just the inclusion of the kernel of B into B, and the second is just B like above, right? Everybody, cool, this is a short exact sequence. Okay. So we now know this gives so here are the induced maps induced by inclusion here, and in particular, this is on to. So the piece I think I want to pull out of this. Notice that in our diagram up here, what we have is alpha is in home. But Sophia is on to, so there's an H here such that B bar of H, speed of H is alpha. And that's exactly here. So, E. All right, so let me give you kind of a, what did I say last? Yeah, so I'm gonna give you a last theorem here before we talk about the tensor product. I will leave this unproven because you gotta do at least half of it in your homework. And it's fun to think about how these maps work. It's got a little bit of weirdness to it. Sometimes I like things that are a little bit weird. So theorem 676. Let A, B, and AI BJ be over models. So all my A's, B's are R modules. If you look at the one, home R, the direct sum of AI, B. So if you look at homomorphisms from this big direct sum of AI and B, this is isomorphic to the direct product of each of the little separate ones. Out of the second variable, it does maybe something that might look a little bit more natural at first. So the direct product pulls out of the second coordinate, I think what you would hope it to. But there's some weirdness going on with the first. So think about, I think it's a good exercise to think about how you would set up these homomorphisms and take it apart. But if you have difficulty figuring that out, please come and give me a holler. Okay. Any questions? Okay. So we've looked at direct products, we've looked at direct sums, they solve certain magnitude problems, right? Direct product, there was this diagram that we have that solves this universal magnitude problem. Direct sum, same thing. Projectives and injectives solve these magnitude problems too, right? How many of you have ever heard of the tensor product? How many of you have seen it in class before? So I'm curious about this. What classes have you seen?
So Macaulay's linear algebra.
Okay. How many of you have had 8530?
I don't know, sorry.
Right, so he did, how much of the tensor product do you do tensor product of vector spaces?
Yeah, nothing over modules, of course, just like
Okay,
vector spaces.
well, tensor products actually come up all over the place. They're so plebeian that even Einstein used them, right? Well, we can argue about, you know, what he was doing there, but anyway. We're going to talk about the tensor product as an algebraic construction. But it shows up, I mean, it shows up all over the place. It shows up in geometry, it shows up in physics, right? from the perspective of an algebraist, this is solving another mapping problem. Only this time it has to do with bilinear maps. So, by the way, let me also give you sort of a disclaimer before I start this off, that you can do tensor products more generally than what I'm going to do with them. And I'll make a note of this as you go along, but what you need is you need to distinguish between left modules, right modules, bi modules, all this non-commutative stuff. It's just, it's not worth me spending all the money on ibuprofen. So we'll just do commutative ring for right now. So let me start off with what a bilinear map is, right? So you all know what a homomorphism is, right? You've been, so imagine that all your algebra has been Calc 1 and Calc 2, and now you're going into Calc 3. And that's what a bilinear map is, right? It's a homomorphism, and if you fix any of the variables, that's what it is. Let me be a little bit more precise here. Definition. Let A, B, and C be R modules. A bilinear map and I'll call it capital F from A cross B and C is a function such that for all all A, I, and A, B, B, I, and B, and R, we have number one, F of A1 plus A2 B is F of A1 B plus F of A2 B. Number two, F of A B1 plus B2 is F of A B1 plus F of A B2. And number three, F of RA B is F of AR B, which is R. Okay, so what does it mean to be a bilinear map? And what was here's my analog of Calc 2. What this first one says is if you freeze the second coordinate, right? So if you freeze B and let that be fixed, then basically that thing behaves like an abelian group homomorphism in the first variable, right? And number two, if you freeze the first variable, it behaves like an abelian group homomorphism in the second variable, first variable frozen. So it reminds me of partial derivatives, right? How you take a partial derivative, you pretend one of the variables is constant, right? And this is sort of the R module bit, right? Because RAB is RFAB. So again, if you've frozen the B, it's R module homomorphism in the first variable, and it's R module in the second variable if you freeze the A. Right? So this is called a bilinear map. Bi because two coordinates, and it basically, if you freeze any of the two coordinates, it behaves like a R module homomorphism. So let me see what kind of. All right. Now what I'm going to do is I'm going to go ahead and tell you. I'm just going to tell you what the tensor product is. the construction, the object. Um, two R lines. And that's the notation that I'm going to use for the tensor product. The sub R on here, of course, emphasizes that A and B are R modules. So definition 6.2. Let A and B be R modules. And I'm going to let capital F be the free abelian group on the set A cross B. Now, this set here is just all ordered pairs, A, B, where A is an A and B is a B. Now, I'm gonna forget about the A and B structure for a moment, and I'm just gonna consider that a set of junk, and I'm gonna do the free abelian group on this, right? So, in other words, you can consider every different one of these A comma B's to be a different, free generator. So this is a very large free model, very big, very big. And I'm going to let K be the subgroup of F generated by all elements of the form. Subgroup. Generated by all elements of the form. Several forms here. Number one, and this might look a little bit, this might look familiar. And C. For three. Where A1, A2, A, and A, B1, B2, B, C, B, and R is in R. Yes,
Why did you write them like that? Can't you just write the first one like 0B or something?
like, run that down again?
Can't we write the number one as 0B? Just simplify.
Zero B. I'm not sure, I'm not sure I understand. So,
Is it?
okay, so you want to write this. Because remember, what we did is free abelian group, now we're portioning out by these relations, right? So every time you see an A1 plus A2, and you subtract this, you're quotienting out of this free abelian group, so you're forcing this relation, right? And the original thing, A cross B, you've forgotten about the structure of A and B, it's just free, right? And this situation right here, what you're doing is you're putting the relations of A and B back on, and you're giving perhaps some extra relations as well. Right? So, for example, well, that's two boards or whatever, but if I did the analog with just one A, right? Then let's suppose that A is Z, and I said, okay, I'm gonna take the three invariant group on Z. Z by itself is generated by one, right? But what I'm doing when I say do the three invariant group on Z, is I'm forgetting about the fact that one and minus one add up to zero. They're just elements, right? So basically, if I had just Z and I did the three invariant group on that set, then what I have is a direct sum of countably many copies of Z, one for each integer, right? But this relation right here will give me my Z back, and also induces some other things on this.
What are these operations plus and minus?
What do you mean plus and minus? So what I'm doing is well, let me finish my thought here, and maybe this will help explain it. The quotient that's mod K is called the tensor product of A and B. Let me point out, some, but let me point out something a little bit practical about what this all says. Well, let me say something. So what the tensor product is you take this three abelian group and mod out by these relations. So this is a subgroup generated by everything A1 plus A2 comma B minus A1 comma B, A2 comma B. So what that does is in the quotient group, it forces this to equal the sum of these two things. Right, that's essentially what you're doing. So notice if you have a particular coset of that form, so remember a typical element of this is actually a sum of things like this, modulo K. If you have an element of this particular form, it's denoted A tensor B and is called a tensor. The tensor product has all the tensors in it, but there's no guarantee that a typical element is a tensor. It's a sum of tensors in general. So think of, so if you like to be practical about this, as the module generated by elements of form A tensor B, subject to the relations. So we'll pick this up next time. A tensor B1, 2 is A tensor B1 plus A tensor B2 and 3 R A tensor B is RA tensor B, or alternatively A tensor RB. So you can think of this, a typical element looks like a sum of tensors. That's what a typical element looks like. It's a sum of tensors, and it's subject to these relations here. So we'll be practical and talk a little bit more about this next time. Any questions? So, yes.
Is the addition defined exactly as the one in A here and the one?
Yeah, that's right, because, so now what you're doing is, so you're taking all elements of this form, you're basically getting your relations in A back, right? You sort of sacrificed your relations here when you took, it's free on the set. But these relations get the relations in A and B back, and you get more, right? So we'll do some practical examples next time. Well, I'll do some competition. I think it'll help the pitch on. Other questions? Yes.
Is a third part a definition or is it a property?
Well, where
Yeah.
we looking here?
Yeah, there, with the third line. Is
Oh,
it-
this right here, yeah, so you can define it this way, R times a tensor is one of these, yeah. Others? All right, well, we will see you all on Wednesday.